Yeah, I can just go with
Yeah, close that. Yeah.
Actually, before we get started, next Wednesday, we won't have lab because we'll have lab Friday afternoon. So, or evening, whatever you want to call it. So there's no point coming here. You guys work on your own time, that's fine. I'm not going to be opening the lab though. So unless you absolutely need the lab open, let me know. But I won't plan on being here because we're going to shift the date to that time. Okay? Definitely you're going to want to work probably on your own and schedule your own work sessions, but there's no point in having it back to back. Because if it was Monday, we might do it, but it's Wednesday, then Friday. That gets a little long. So, any questions about that? No? Okay. So as we were talking about it, we really want to develop this way to set these joints up so that, again, they ramp up, like we talked about before, but that ramping is going to be smooth, right? So let's kind of look at a couple of different things and get the basic idea of trajectory planning. So let's go ahead and call this trajectory planning. And so the idea is, here's our x-axis. Just assume this is going to be a robot arm. We're looking down on it, kind of thing, if you want to say looking down on a two-joint arm. And we've got this one joint, or this one link right here. We call this link 1 or link 2. And it's currently, initially, is at 20 degrees. Then I've got another one, another link, which is starting at 30 degrees. Okay. And it's going to have some length, L. We're not really worried about that now anymore. So, I mean, if you look at this, when we were doing, chapter 5, we started with this very model, right? We did the Jacobian off of this model. Then we did Lagrange off of this model. Now we're going to do the pathing. So we've seen this model quite a bit. But now we're going to talk about trajectory. So again, when we talk about trajectory, that implies what?
Timing.
Timing. And timing implies what? Velocity, accel, blah, 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 right? Okay, so let's talk about the timing. So the question is, how should we move each joint? So if this is my starting point, let's say this is A, and let's say this is B, I want this ending joint to be here. But now I can't, if I look at this, if I swing this around right here, this is going to be too long, won't it? So what's going to happen is my ending joint for my inverse kinematics, it says that my final is 40 degrees, and that this joint, pretend they're the same length in the picture. Like, let's go ahead and make that a different color. Let's give it a target. This ending point is 180 degrees. I'm sorry, not 180, 80. So it's almost 90, it's close enough. You get the idea in the picture. It could be 90, if it were 90, then that 40 could be 30, for example, right? Whatever. This is what the inverse kinematics that we've understood now result in. This is my destination. So then I can figure out the path profile for velocity, mean, let me say back up for a minute. I know how to describe the joint velocities to get here because the inverse convection gave me that. My Jacobian explains me that, right? So I have my Jacobian matrix, I have my destination right here at a certain velocity that travels from A to B, such that I don't exceed the torques based on my Lagrange, right? So now the question is, how fast should this go, right? So let's give it some timing. So we give it some time specs. So let's say there's A, and let's go ahead and call this guy alpha, and let's call this angle beta. Okay. So I'm going to have time, alpha, and beta. And this is my end effector velocity. The frame from A to B. Everything we've been doing, so that's my D vector. Remember we did that in chapter 5. And these guys are my joint space values. So at time 0, alpha is going to be at 20 degrees, and beta is going to be at 30 degrees. So far, so good. Let's go ahead and break this into 1 second epochs. 2, 3, 4, which is nothing more than a fancy way of saying intervals. And we're going to say we want to move at a rate of 10 degrees per second. Okay. No faster. And we've done that because maybe we want to limit our torque, right? Or maybe we haven't thought that far ahead, to be quite honest. Which one's going to have a higher torque load, alpha or beta? Beta. Try again. Must be alpha. Right? Because this guy's got to carry his load, right? So he's easy, right? This guy's got to carry all this stuff and all of his accelerational forces, right? Coriolis, centripetals, etc. Plus the loads and gravity. So alpha's got a lot to do, right? So it's going to go 20. It's going to move at 10 degrees per second. So it goes to 20, goes to 30 degrees, and it gets to 40 degrees, and it's done. So it goes 40, 40, and 40. Okay? And why did I pick 10 degrees per second? Because I'm going to go in 5 seconds. I said, so my timing, I said, it has to occur in, you have 5 seconds. To move from A to B. All right. Which means the rate is going to be the 10 degrees per second. So that means I'm going to be at 40 degrees, at 50 degrees, 60 degrees, 70 degrees, and my final destination of 80 degrees. Seems okay, right? So yeah, all right. But again, where is my fundamental load? In fact, let's go back before I even get to there. So if I were to look at this, I could see my intermediate. Whoops. So I'm at 20, and I go to 30 and 40, right? So that's my final. This guy, on the other hand, 1, whoops, yeah, 2, 3, 4. Try that again. 2, 3, 4. Assume it's even angle. But that's the idea, right? It's sweeping across. Theta 1, joint theta 1, is going to incur significant force, right? It could. And when I say significant, significant relative to what I could be. Because let me ask this question. It's got all that load and I have to accelerate 0 to 20, or 0 to 10 degrees per second. Right? I have to get there moving pretty good. I got all that torque. Maybe I can't move theta 1 at that rate. Even though I implied that I'm using 10 degrees per second for beta, once I get there, I just sit there and wait there for the next several seconds after here, right? Wait. Did I have to wait? No, right? I didn't have to do any of that. I could be a little smarter in how I do it. So I could break up. I could reduce.
Professor, what is it said right there? Like in joint theta 1?
Joint theta 1 incurs significant torque.
Oh.
To reduce the torque at joint 1, we can reduce our rate of theta dot. So we could actually we have to go 20 degrees. We have 5 seconds, so we only can go 4 degrees, or have to go 4 degrees per second for joint 1. Right? Why do I have to make it go 10 degrees per second and have to wait? I can just divide that out and say, I'm going to go 4 degrees per second. Right? That seems plausible. And so we're going to call this a uniform distribution. We're going to uniformly distribute the velocity for each joint. So if we do that, then we're going to have time alpha and beta 0, 1, 2, 3, 4, 5, 20 degrees and 30 degrees. And we're going to go 40, 50, 60, 70, and 80. But now we're going to go 24, 28, 32, 36, and 40 degrees. And so we see that we have a uniform velocity. Constant, right? We say uniform, we also mean constant. So far, so good. Okay. But when we look at these velocities, notice these may in fact not, even though this is uniform angles, this distance may not be uniform distance. So yes, we're looking for the joint space, but are we really looking at the behavior of the end effector? And the answer is yes, we really want to know the end effector behavior more so than the joint behavior. In other words, while the joint behaviors are easy to control, and if we want to make their controls easy, that's fine, but it may not give us the desired results for the motion profile that we're looking for the end effector, where we might want that to be smooth instead. We may not get the smooth motion out of the end effector. Well, we might get it here. This end effector may not be. And ideally, we want to do this at the cost of making this harder, yes, but this is really what we're trying to control. If I have some very fine precision requirements on that end effector, I want that to be fine. Who cares what this has to do? Figure that out. That's your job. Get those joints to work however we need to do such that end effector is looking really good. Who cares if it makes this part hard? Yes, this is easy. Yes, the other one is easy, but that doesn't mean it performs better on the end effector. And it won't. By the way, before I go on, I know I haven't typically been lecturing using this. I'm particularly using this style of lecture on this material because I think it makes a better fit. Because we're doing much more math, but we're deriving without a lot of pictures. Fair? Do you guys prefer this? I'm just kind of curious. Do you prefer this or the PowerPoint style?
I like this.
You like this for this topic?
Yeah.
So would you want to see this topic in the PowerPoint or keep it in this format?
I keep it.
But the other stuff, were you happy with how we did the other stuff? Where I kind of gave you just the boxes to fill in? Because there's a lot of pictures and diagrams to draw. Yes, no?
Yes.
Because there's no slides, there's no source notes kind of thing to look at, pre-read, but this stuff's pretty straightforward in a way, especially in the book. So now what we have is, suppose instead of favoring the joint velocities, we favor the end effector. I'm going to say the end effector path / trajectory. So again, the path doesn't have any type of timing information, but it's going to maybe be uniformly distributed. So that I could have a path that might look like this. And I'm going to draw this at a slight angle this time, just to kind of illustrate the point. We want to as we go A to B, each one of these distances, so this is like I say, t equals 1 second, t equals 2 seconds, t equals 3 seconds for this guy, t equals 4 seconds, t equals 5 seconds. So that the distance at each second is constant. So that is, each one of those is L, so that means L1, L2, L5, so that L1 is equal to L2 is equal to L3 equals L4 equals L5. Equal limits. And if you do the math, you do the geometry, like let's say we're in here, our goal destination, looks like this, and our in-betweens, we're starting here, but our second one may actually drop down a little bit. And then, so this is going to be maybe this is our original, this is, say, our first. And then we're going to have, actually it's going to drop a little more than that. Let me be a little bit exact. Let's go down to here. And this number 2 is here. 3 is going to be here. 4 is here, and then 5 will be here. And then we see, whoops, that this guy would be here. If we do that, then if I look at my time, my alpha, my beta, and I do the geometry, which I won't bore you guys on. 0, 1, 2, 3, 4, 5. Our alpha angle, we start at 20 degrees, and we start at 30 degrees. We drop to 14 degrees to maintain this profile. So we go from here to here, because that length is fixed, that shoulder drops down. Then as it goes up, it's lessened as we slowly start to bring it out. So again, bear with my drawing, my apologies. All you guys who draw really good are probably laughing at me, that's okay. I'll take it. It's just illustrative. So we go 14, and then we're going to go to 55 degrees. And then we're at 16 degrees. And then we go to, I'm sorry, that's a 55, not a 50. Then we go to 69 degrees. And then we're going to have 21. And that's going to result in 77 degrees, 29. And that's going to be 81. And then we're going to have 40. So actually this kind of goes overshoot there. Right. And then our last one will be at 40 degrees and 80 degrees. Wow.
It's 20, and the next
20
one is?
and drops down because that's such a short distance. I have to account for that length as it moves up, and so that has to kind of go down. As this goes here, that will drop, right? And then drop a little bit more, and then they both kind of move together.
It's 14, 20, 14, 16,
16,
21.
29, 40,
Okay.
yeah. Now, what's important, so this is our positional, right? This is our positional displacement. Our joint positional displacement. And our positional displacement, if we look at this, that's a distance of 6 degrees. Now, it's a distance of 6 degrees, but it's going to go negative. It's going in gravity. It's like, who cares? Right? I'm not fighting gravity on that acceleration. So, okay, it's doable. And then I have a distance of 2 degrees to travel. All right, and then I have a distance, or a delta of 5 degrees. A delta of 5 degrees. All right, it's not too bad. I'm sure that's a 7. That's 8. And I have a delta of 11 degrees. Now, that's a big jump in 1 second. That's more than I had to do before at 10 degrees per second. Now I'm at 11 degrees per second, aren't I? And on this side, it's not nearly as bad, or is it, right? So it's 30 to 55. I mean, that's 15 degrees, right? And then I have 14 degrees. And then I have 8 degrees. And then I have 4 degrees, and I have 1 degree. Not as critical, because it's the lesser torque joint, right? But I just gave myself a 15 degree per second velocity. Wait, I said I could only go 10, didn't I? So, you know, while the displacement of the end effector is constant. It forces large torques let me say this one, there are large velocities, velocity differences which is going to imply large accelerations, which implies larger torques.
Good question.
Yeah.
When it goes to 81 degrees, are you trying to like show us like it'll overshoot and then adjust?
It has to because of the physical length of the arm itself, just to make the geometry work out. So basically, if we do the inverse kinematics from chapter 5, remember you guys do this really simple inverse kinematics, or even chapter 2, we did the inverse kinematics of that arm, in fact, right? That's when we did it. If we do that for the two thetas, that's what we're going to get, forcing that length to be constant, right? Instead of moving each joint, we're saying I want this L for each second to be the same L along that path. Not trajectory, along that path. The trajectory is the wind. We want that to be uniform, but that path we want to have equidistant L's for each second.
So you're covering path planning right now.
This is path planning, trajectory planning. They go hand in hand. Trajectory planning is path planning with time.
Okay.
So we were given, when we talked about the inverse kinematics, we never talked about how we were going to get there, what path we were going to take, what route we were going to take at the velocity to do that at. Right? We said, okay, well, this is our solution. Our inverse kinematic says we're going to go to here. Okay, but how do we move each joint in order to do that? Knowing that we have these other constraints. So what we see is perhaps constant L is a bad idea. I think we all agree, yes? So, what are my other options? No one wants to take a guess? Instead of constant L, we could have a displacement. I'm just going to draw the displacement line if that's okay with you guys. So let's say this is point A and this is point B. Put it in any orientation you want, doesn't matter. Initially, I might have a small one. And then it's going to get bigger and it's going to get bigger and do something like that. I can even break it up into smaller joints or smaller sections. So I have 1, 2, 3, 4, 5, 6, 7. Not necessarily seconds, but just lengths. I still have the 5-second time span. But instead of breaking it into one per second, let's be smarter about this. And so if we look at these displacements, we see what? What do we, if I drew that pretty accurately, I think it looks pretty good. What would we look at from a displacement profile? It's parabolic, potentially, right?
Parabolic.
What's that?
Like, I
It's squared. So the distances get bigger, but they start off smaller. They get bigger distances, and then they get smaller.
That is yeah.
Right? So my profile displacement so the lengths are scaled parabolically. So if I were to look at it from a displacement graph, so this is time, and this would be profile displacement. I'd see something that's looking like this.
Oh, does it return to the starting position?
This is going to be displacement. So this is the displacement L. So it's going to go to B, point A, point B. But the jumps, instead of being uniform jumps, they're small jumps. And they get bigger and then they get smaller.
Oh, okay, I see what you mean. It accelerates and then it decelerates.
Right, exactly.
Okay.
So we said, although that's displacement, we can do that also for the velocity accelerations. So we can define the trajectory in terms of our theta in a polynomial order. So that that's displacement profile, but we can also extend this so that we have velocity and as needed, we could go to acceleration where we had the same idea. So we could have some higher order displacement derivative i.e. velocity. You could do velocity. We could do acceleration, et cetera, where we have something that might look like this. Which is what we talked about yesterday on Monday, right? We're going to ease into it and come down to it. Preventing this type of action. So instead of, I can still make my end effector uniform as far as, say, their velocity or their acceleration. I can make it smooth and allow that these can now be smaller displacements by not having these big jumps. By just going here, 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 here. I can control them. I can create a polynomial that describes this. Moreover, we've been looking at the profiles, a profile, in 1 second periods or intervals. Right? In other words, what we've kind of been doing is we might be looking at something that looks like this. If we just think of it from a positional perspective, not just this is some just in generic form. Well, I've got this and I've got this. It is what we call a piecewise linear, potentially.
A bunch of tangent lines.
Yep, exactly. So piecewise linear. So they're just these segments that we stack together every, say, second or whatever. But the reality is we want something smooth. I kind of did that too good. Let me exaggerate this. Straight line, straight line, straight line. That still looks too good. I'm gonna, yeah, I guess so. Is that fine?
Yeah.
Okay. What we want is that, right? We want smoothness. Now, piecewise linear is exactly that. It's a line. Right? It's AX plus B, right? There's my linear part right there. Bunch of lines. That's all we mean by a constant or a linear relationship. But what if we want something smooth, so how do we get to that smoothness? This is going to be not just x to the 1, but we need higher order polynomials in the positional time derivatives. Higher orders of polynomial motion. So higher orders of positional time derivatives describing motion. Right, so that implies we could do quadratic. Oh, there's no t. Quad. Right? I could do a third order. I could go to a fourth order, a fifth order of the positional time derivative. We did this in high school physics and high school calculus. Right? What's the time derivative of position? Velocity. Right? So what was that going to be? So what is velocity is equal to?
Linear function.
D is equal to velocity. In terms of velocity, D is equal to VT, right? So this is my first order polynomial. D is also equal to, oops. I'm going to forget the plus, I guess, D naught, right? Plus D naught. I can also say it's 1/2 AT squared plus VT plus D naught, right? And we can ignore that. Let's just call it K0. Let's call that K2. K2, K1, we can call this guy K0. I can also say that D is equal to K3T cubed plus K3T squared, I'm sorry, K2T, let me give myself more space. D is equal to K3T cubed plus K2T squared plus K1T plus K0. All of them describe a displacement with the time derivative derived from this position. Right? We take the derivative, we get to the velocity. Right? Take the second derivative, we get to the acceleration. Third derivative is the jerk, so on and so on and so on. Right? So I get the nth order time derivative of position to create a polynomial to describe my velocities. Now all of a sudden, all I now have to do is just find all my K1, K2, K3, K4s, etc., such that D is satisfied for the time interval required. That's all. He's got to find all the K's. There's only a bazillion of them. So if we write this in terms of theta, we can construct an expression for theta as a function of t using coefficients for each time polynomial power. This implies, or this requires, will require some initial conditions to be defined. The initial conditions I'm talking about is my starting position, my starting velocity, my starting acceleration, my starting jerk, my starting et cetera, et cetera. Okay? But we can write our displacement theta as a function of time, where we have C naught, our initial position, plus C1 t, C2 t squared,
That's it, right?
C3 t cubed, exactly, it doesn't matter. For time initial to time final at some initial theta to some final theta. Oh, sorry, this isn't T5, this is TF. So at an initial position, we'll have an initial time. From a final position, we'll have a final time. And the reason we can say that is by saying by defining an initial and final, we can create motion profiles for path trajectory segments. In other words, I can define, suppose I have a segment that goes from here to here. Then I have a segment that goes from here to here. Very distinct segments. So this is theta to theta, theta to theta, theta to theta. We'll find eventually that we can have the acceleration from this feed into the acceleration to this, or that the velocity will carry through from segment to segment to segment. But we treat the trajectory, we treat this single trajectory as an acceleration, a jerk, etc., to a deceleration, to a de-jerk, etc. But this velocity that we end at right here, we may not necessarily want to come to a stop. So if this velocity, say, is 5 degrees per second, the next one is 7 degrees per second, why do we stop going from 5 when we can maybe have them continue onward but now go faster? Why stop and then continue to go? Right? So the input velocity of this next segment could be the ending velocity of the first segment. And so on as we move down nice smooth trajectories.
To reduce the number of inflections.
Well, what we're able to do by that is reduce the number of decelerations, which reduces the number of accelerations. Because we're already moving. Why go to 0 when we didn't have to go back up again? Depending on what we're doing, right?
Like seamless.
So it's seamless and smooth. Exactly. Because when we have those discontinuities in motion, what happens to our torques? We saw that in Capelli ascend, didn't we? It spiked up and down because we had that discontinuity in our motion profile. So to alleviate those spikes in our torque requirements, we need to have smooth motion profiles, smooth accelerations, smooth jerks, smooth whatever the fourth orders are, fifth orders are, sixth orders, seventh orders, along the time. Okay? So when we come up with this motion profile, we can become very smart at how to do it. And so what we see here then is we define our initial conditions. All right, so given, let's go to the third order. The theta of t is going to be, again, C naught t plus C1, sorry, there's no t there. It's t to the 0, right? C1 t
plus C2 T squared plus C3 T cubed. Initial conditions. In fact, we can do a different color for that to help differentiate. Green. We want to have, and final conditions, say in bold, right? So theta at T initial is going to be theta initial. Theta at T final will obviously be theta final. Now, theta dot at T initial, so my starting velocity, it could be a velocity coming from a prior segment. It could be starting from rest. It could say, we're done moving, our final velocity is done moving, hence 0. So it depends on what we're doing, right? So in this case, we're going to say that our theta velocity, or theta dot initial at time 0, or the initial time, is going to be 0 degrees per second. And we're going to say that our theta of T final is also going to be 0. In other words, we're not moving. We're going to come to a rest. And this is the motion profile for joint 1. Motion profile for joint 2. So in our previous example, we had a motion theta I was 20 degrees, theta final was 40 degrees. We had theta 2 at 30 degrees initial, theta 2 final was 80 degrees. So we do this for each joint. So we started off looking at the big robot. Then we said, okay, let's look at the velocities down to all of the joints to the end effectors. Then we looked at the torques for all of them. Now we're looking at a particular joint, realizing that this applies for each joint. So as you're building your arms and you're trying to get good control over them, don't just turn it on and say, go to this velocity. You know the destination position, give it 5 seconds or how long it's going to go, you're going to say, you have 5 seconds, or maybe you can set T so that all the joints don't over accelerate, but we can give it a motion profile at the same time so we can have smooth accelerations. We can have reduce our accelerations by controlling our jerk. So we can control velocity, we can control theta dot, we can do a control the theta double, triple dot, a control for theta fourth dot. We can have a higher order time derivative position controller to what we need of that nth order positional derivative. And I say positional derivatives because that's what we're talking about. It's theta dot, right? It's with respect to time. As opposed to the partial, which is a Jacobian, which is related to another joint value or another position value, x or y, so another variable. This is all with respect to time because we're dealing with motion profiles, because we're dealing with time, because time is trajectories, because trajectories are paths with time. Everybody good on that? I kind of like lecturing with these chairs. So, okay, so if this right here is our theta, then what is our description of theta dot t? Well, that's pretty trivial. So, I'm debating. So we have that. I'm going to write in the same format. Theta of t, theta dot of t
equals, and I'm going to write it in such a way that it lines up over here. So I have C1, right, just take the derivative of theta, right? So it's pretty simple. I have C1 plus 2 C2 T plus 3 T squared, whoops, C3 C3 T squared. Right? That's pretty easy. Right? Again, this is all calculus. This is like, so I was talking to somebody the other day, and I said, we were talking about math. They said, I think you were talking about calculus. I said, I think calculus is the easiest class in math. Calculus is the study of what? Anybody know this answer? I remember taking my calculus class, and it dawned on me what it was back in high school. This is easy. Once I realized all calculus was. What is calculus the study of? Anybody want to venture a guess? Not time. Calculus is the study of change. That's all it is. All calculus is the study of time, or study of change. With respect to time, with respect to other variables. And once you realize that the slope is nothing more than describing the time relationship in a linear fashion by one value, it becomes easy. A parabolic is looking at two values of change, right? It's the first change and the change of the change. And then you have the change of the change of the change, that's the impulse. The change of the change of the change of the change. When you guys drive your cars, you're doing calculus all the time. You're looking at the cars next to you, and you're not looking at you're going a velocity, so you're already going a rate. You're already going a first derivative, if you're at a constant velocity. The car next to you, that distance between the two of you isn't changing. They're going the same change that you're going, right? Now, in California, we think we own the road. In California, we think we own the gap between us and the car. We're always trying to get ahead of that gap. And everyone's like fighting for that gap. We're living for that gap when we drive in California. You go elsewhere in the country, it's not so much. But California, that's my space. Screw you, I'm defending that space. That's mine. Don't think you're going to take it. Now, it really sucks when we're on a 2-lane road, and I got a semi coming up on my right-hand side, right? I got that stupid Tesla who says, oh, I'm entitled to not have to stay in line because there's a gap up there. Y'all can recognize and sympathize with this, empathize. And so what does that Tesla driver do? If you guys drive Teslas, I apologize, but you know you're the worst driver. Just kidding. It's just they just get a bad rap because it is not all Tesla drivers are, but Tesla drivers on 15 going to Vegas are the ones who are always doing this. My experience. What do? You're in line on the left lane, right? We're just all cruising along, going a constant velocity, a constant change of position. Yes. We're all set cruise control. We're all going about 82, right? Typically. And the semi's on that right-hand side going 75, right? How do you know he's going 75? Because the distance between him and you is decreasing. You're at a higher rate than he is. That change in position, that distance is changing as that function linearly. But what happens to that gap? Where's that Tesla? What does that Tesla driver do?
That doesn't speed up.
He can't. Well, he can't speed up because he's behind you or behind 2 cars back. So what does he do? Lane change. He's going to change to the one behind the semi, isn't he? And then what is he going to try to do? He's going to try and get ahead of us, right? He's going to accelerate, right? So he's now going to go faster than you. So he's going to do a change of the velocity relative to you. Right? It's the first derivative to you, but it's the second derivative of the position. Right? He's accelerating. In fact, he's not going to even accelerate constant. He's going to accelerate at a rate. He's going to change how fast he accelerates. He's going to increase. Right? He's actually do a non-constant acceleration as that gap closes because he thinks he owns that stupid gap. Right? And then what happens? You're going, hell no, and you accelerate. Well, I'm not going to get cut off. Because that's really what it's about. You just don't want to get cut off at the last minute. So everyone's sitting there jockeying up behind it. The guy in front of you takes off going, oh shit, I'm going to lose my spot. He's going to cut me off. So now I got to get on top of him. And then everyone's trying to box it in that stupid Tesla who said, why didn't you stay in line with everybody else? You're not special. Am I right? What do we do? So we all managed that gap, didn't we? We all managed the displacement distance between that. The change of that distance is really what we're now managing. Calculus is that. We drive doing calculus without even doing it. We instinctively understand calculus, which is all this is, right? This is trivial. Because once you realize that's all calculus is, calculus becomes super easy. The change, John's just like saying, no, I'm not buying it. Huh?
I said, I'm not having any of it.
Calculus is easy. When you drive, you're doing calculus intuitively. Because you go through that entire thought process. Yes, you're not taking the derivative. You're not saying, okay, here's my d, here's my x. Let's come up with an equation of motion and derivative, blah, blah. You're not doing that. I get that. But intuitively, you are doing that when you drive. Because you're watching that gap. You're watching how fast they're going and how fast you're going. And you're managing that displacement of using your acceleration, your velocity, your impulse, the derivative of your acceleration. Am I right? Or am I the only one who thinks like this way when I'm driving?
That's going to be all you.
Huh? I'm not necessarily doing a derivative. I'm thinking, I'm not letting that guy get ahead of me and cut me off. That's what we're all thinking, right? That's what I'll get at. But how do we manage that? We control our accelerations, right? But that's calculus. That's all it is. That's all this is right here. So we've done this a bazillion times when we drive. We just don't sit there and think taking the derivative. That's what's going on. Intuitively, we know that. Intuitively, that's what we're doing. No one put a word to it and say, oh, you're doing calculus. That's all calculus is. It's the study of change with respect to time and or another variable. So now that I just compiled like what 6 classes into one sentence, might give you some perspective. I'm not going to belittle the classes; they're important. Don't get me wrong. But we need to figure out. We need to find our coefficients. C1, C2, C3, etc. So we have these initial conditions. Our initial condition is going to be, we said that our theta Ti is equal to C naught, which is equal to theta initial, i.e. at T equals 0, right? And that our initial velocity at Ti is going to be C1 is going to be 0. So like again, we look at this, our initial velocity right here, T is equal to 0, goes away, initial C1. Right? If you want to say, where'd you get C1 from? Because T is at 0, T is at 0, 0, 0, we're left with that guy, right? So, okay. So now, again, going back where we have our equation of motion, or fundamental equation of motion that we have right here. I'm just going to go ahead and rewrite this. So I have theta of T is equal to C naught plus C1 T plus C2 T squared plus C3 T cubed. Theta dot of T is equal to C1 plus 2 C2 T plus 3 C3 T. In fact, let me do it this way. No, that's fine. I'll write that way. No. Do I want to shift it there, or do I want to not shift it?
Just
No, we'll leave it like that. Okay. Now, we want to find our C's. In other words, what we want to do is we need to solve for C's, but we know a couple of things, right? So we have our theta initial, our theta final, our, let's do it this way. Theta initial I, it doesn't really matter, but it makes it easier this way. Theta dot theta final, and then our theta dot final. I want the C's. I have expressions for all of these terms, theta 1, theta I, theta F, theta dot I, and theta dot F. I'm looking for C0, C1, C2, and C3. I can create a linear matrix or linear system of equations for the relationships to solve for my coefficients. So theta I is equal to what? We already said it already. Is equal to C0, right? So it's equal to C0. So theta I equals C0, right here. Remember, it's this times this plus this times this plus this times this plus this times this, right? So I got C0. Do I have any C1s to define what this is right here? I'm looking for this. And we're going this times this plus this times this plus this times this plus this times this. To solve for theta I, all I have is C0, right? Do I have any of these other C's? So what should these be right here? 0. Get rid of that plus, it's wrong. 0, 0, 0. Okay. Theta dot I equals C1. I should say not add equals. But it's still C1, right? So I have 0 C0s. I have 1 C1. Do I have any C2s? Do I have any C3s? No. Again, this is at time equals 0. Okay. How about theta F? Does theta F, when we're solving for theta final, right here, so now theta final, do I have a C0? I do. I have how many? I have 1, right? How many C1s do I have? How many C1s do I have?
1.
I have T's.
Oh, T.
Right. How many C2s do I have? T squares. How many C3s do I have? T cubes. TF cubes, in fact, right? So this is final. At final, I have that much in front of me. How many C3s do I have for the ending velocity? I got 0, right? How many, what's my coefficient for C1 for final velocity? 1. What's my coefficient?
2t.
2tf. And
3e squared.
Oh, it's supposed to be square.
Yes.
Square. Up top.
Up top, up top.
Theta dot.
oh, yes, thank you. I have it in my notes. And this is equal to 0. Our final velocity is equal to 0. We said so. So I know this. I know this. I know this. I know this. I know TF. I know T. I know all my T's, right? I can do this for any T. It's like 5 seconds.
And my velocities, my velocities, starting velocities, ending positions, final positions, or start and stop positions, start and stop velocities, duration, or more importantly, this is a function of how long I ran T for. So that means I can solve that. We could simply say that let's just call it theta is equal to some matrix times C. C is my vector of coefficients. Matrix is my matrix that relates those two together. And this is my starting, ending, positional information. Could be my nth order time derivative position, first order, second order, whatever I want. So I can find, so we use our initial conditions to define theta initial, theta final, theta dot initial, theta dot final time to get C. So that if I do my matrices, I'm going to get inverse M times theta is going to equal C. Or you might actually write it like this. So you have C, the coefficients become M minus 1. Givens, figured out it, answer. Once I have my coefficients, at any point in time, so once we have our coefficients, i.e. C0, C1, etc., then we can find theta of t and theta dot of t for any time defined by that interval. What do I mean by that? This is my equation of displacement. This is my equation of velocity. Once I know my C's, I can put in, what's my position at time equals 2.4 seconds? I gave my interval 0 to 5 seconds, for example, right? So all of this was calculated based on a 5-second duration. Fair? What's my velocity at 2.4 seconds? I don't know. Or what's my displacement? Where am I at on my theta? I plug in my t, 2.4. I already know my coefficients because I found them right here. I know where I'm at. How fast am I at that point? I plug it into my theta dot. I could actually find my accelerations as well. I could take another derivative, time derivative of this, right? Theta double dot. That goes away. That's going to become 2c plus 6c3t, right? That's my acceleration at that point on that trajectory. Pretty cool? How are we doing on time? I think we're almost done. Yeah, we'll do an example. We'll do an example on this on Monday. Does that work for you guys? In fact, on Monday, I'll show you a MATLAB file that I wrote that does all this for you. Because at the end of the day, this is actually pretty straightforward, right? I can do this the entire time for a given path and go, well, what if I go to a third order, a fourth order, a fifth order, a sixth order, a seventh order? What does my values of acceleration look like? If I know my accelerations, what can I also know? My torques. I can play games with torques by simply saying, you know what? We're going to go to a higher order polynomial. Because instead of just going straight up, we're going to kind of ease into it. And it will taper off. So a second order is just going to do this. A third order is going to give you another point of inflection in that trajectory. A fourth order is going to give me a double parabolic behavior. A fifth order is going to give me more wiggly. In fact, I can use my polynomials to define something that looks like that. I can use my polynomials so we can therefore define theta of t using polynomial. So again, we see a second order. We could see this as a second order. We could see a third order like this. We could see a fourth order. So a cup, right? That'd be a fourth order. I can go all the way down defining these different characteristics, right? This is my point of inflection. This is going to be that inward, right? So we see that parabolic behavior. Here's my point of inflection because this is a third order. That double cupping is a fourth order, etc. I can extend this to a seventh order polynomial to get one complete profile in position. Seventh, and we'll do that. That's one of the examples we'll do, is trying to go up to a fifth order. Do you guys want to do an example real quick on this, or are you guys brain fried? Brain fried? Don said I'm done. So what I'm going to do is I'll do the example on Monday, and then we will wrap everything up on Wednesday. We're making good time on this. We'll go to the fifth order. Yeah, we'll do the example. And so here's the one thing that we can talk about. Let me just kind of paint the picture of where we're going. Imagine seventh order polynomial. You can kind of see how a seventh order polynomial could get there, right? We got to figure out a whole bunch of C's to get there, or maybe a fifth order. We got to figure out a whole matrix, but it's not that hard. All you need are the initial conditions. Suppose we only care about higher orders where we have transitions in our velocity. Once we're at constant velocity, I can go to a second order and call it a day, or a third order and call it a day. So I can make sure I have no acceleration. I can control my accelerations. I have a third order polynomial. Control my acceleration to be 0. Control velocity to be constant, right? My control system can do that. But when I'm starting up, I might want to have some really good fidelity in that polynomial. So I might want to do a fifth order or a fourth order polynomial to maybe a third order polynomial to a fourth order polynomial. So I can create these segments that these are going to have these blending points. It's like when this fifth order finishes at some point in the displacement, hence at some point in t, I switch over with that input velocity, that input position, into a third order polynomial. I get after my destination, so this is my airplane model, right? I'm taking off. I'm going to fifth order polynomial, describe that takeoff. I'm cruising. I don't care what my fifth and sixth order terms are, they're zeros. All right, I'm going to come in for my landing. All right, let's turn on those higher order polynomials so we can really get a good smooth function as it comes down, comes in and describes that behavior at a fifth order. that input velocity is no longer zero. When I started, input velocity was 0, acceleration being maybe limited, maybe my impulse is limited. I get to here, I got an ending velocity. I don't care about anything else. That's my input velocity out of this segment. I'm done. I have an input velocity into this segment. I'm going to come in for that landing following a fifth order polynomial. So I don't necessarily have to do a seventh order to describe that whole profile. I can do a blended trajectories, or I can blend a fifth to a third to a fifth, or a fourth to a third to a fifth to a fourth trajectory profile. That's what we'll talk about next week. So we'll go through examples on how we do that. It's pretty straightforward. It's very cookbooky, and I'm going to show you guys also how we can see what this looks like in MATLAB using some files that I give you guys. Okay? So we do have 2 packed lectures next week. Not going to deny that, but it'll be complete when we get done. Does this all make sense?
Yes.
All right. Lecture is over. You guys are free to work in here on your own. You're free